Across the vast expanse of our universe, galaxies take on a breathtaking array of forms and sizes. Among the most visually striking are the so-called flat galaxies, those slender, disc-like structures that seem to defy the chaotic swirl of cosmic matter. The thinness of these galaxies and their tendency to form in elegant, planar shapes is not merely a quirk of nature. It's a manifestation of the intricate dance of gravity, angular momentum, and the history of their formation. When we peer into the night sky, our own Milky Way is the quintessential example of a flat galaxy. From our vantage point within the disk, it stretches across the heavens as a hazy river of stars. But why do galaxies like ours and countless others settle into these thin, flat configurations, rather than forming more spherical or irregular shapes? The answer lies in the way galaxies are born and evolve. In the early universe, immense clouds of gas and dark matter began to collapse under their own gravity. As they contracted, any tiny amount of spin, any initial angular momentum became amplified. Like a figure skater pulling in their arms, the rotation sped up as the cloud shrank. Over millions of years, the collapsing material flattened out into a disk, where centrifugal forces counterbalanced the inward pull of gravity. Stars, gas, and eventually planetary systems settled into orbits within this spinning disk, leading to the flat, spiral structures we observe today. Yet not all galaxies are so orderly. Some, like ellipticals, are more football-shaped, the result of violent mergers and interactions. But in regions where galactic collisions are rare, the quiet, persistent influence of angular momentum reigns, preserving these elegant disks for eons. Understanding why galaxies are flat is more than an academic exercise. It tells us about the conditions of the early universe, the role of dark matter, and the gravitational ballet that governs the cosmos. It also lays the groundwork for understanding how solar systems, like our own, form within these galactic disks, inheriting that same preference for flatness. As our understanding of these cosmic structures deepens, humanity's ambitions in space continue to expand. The future of the space race, once defined by the Cold War rivalry between superpowers, now enters a new era marked by international collaboration, commercial innovation, and the tantalizing prospect of tapping into the resources of other worlds. Recent years have witnessed a dramatic acceleration in space exploration. Government agencies like NASA, ESA, Roscosmos, and China's CNSA are pushing the boundaries of what's possible, while private companies such as SpaceX and Blue Origin are driving down the cost of access to orbit. The Royal Society's recent Space 2075 report envisions a future where space activities are not only routine, but transformative. Within the next half-century, we may see asteroid mining operations, factory-sized manufacturing plants in orbit, and even the birth of new communities beyond Earth. Central to this vision is the concept of an off-world economy, one where we extract, process, and utilize resources found beyond our home planet. The Moon, with its proximity and rich deposits of water ice, is already a target for early mining efforts. But perhaps the most ambitious frontier lies further afield: Mars. Mining. Mars is no longer the realm of pure science fiction. The red planet holds vast reserves of minerals, metals, and, crucially, water locked within its soil and polar ice caps. Unlocking these resources could enable sustained human presence on Mars, provide fuel and life support for deeper space missions, and even deliver rare materials back to Earth. But the challenges are enormous. Mars is over 50 million kilometers away at its closest approach, and its thin atmosphere offers little protection from radiation or micrometeorites. Traditional mining methods, honed over centuries on Earth, must be radically reimagined for the Martian environment. Recent advances in robotics and artificial intelligence are paving the way. Research groups are developing autonomous robot swarms capable of constructing habitats, extracting minerals, and processing resources with minimal human intervention. These robotic pioneers could work tirelessly, preparing the ground for human explorers and settlers. The implications of Martian mining extend far beyond the pursuit of wealth. Extracting resources on Mars could dramatically reduce the cost and complexity of sustained exploration. Water, split into hydrogen and oxygen, becomes rocket fuel, enabling spacecraft to refuel for journeys deeper into the solar system. Local materials could be used to build shelters, grow food, and manufacture essential supplies, lessening our dependence on costly resupply missions from Earth. Yet, as we contemplate the potential of mining Mars, we must also grapple with profound ethical and environmental questions. How do we balance the drive for exploration and resource utilization with the need to preserve the pristine environments of other worlds? What legal frameworks will govern the ownership and exploitation of extraterrestrial resources? These questions are already being debated by policymakers, scientists, and ethicists around the world. Meanwhile, the broader space race is evolving. No longer limited to government agencies, the new space age is a tapestry of multinational partnerships, commercial ventures, and visionary entrepreneurs. As the Royal Society's report suggests, we are on the cusp of a new era, one where space is not just a destination for exploration, but a domain for commerce, industry, and even habitation. Technologies once imagined in science fiction are becoming reality. Autonomous mining robots are being tested in analog environments on Earth, refining the techniques that will be used on the Moon, asteroids, and Mars. Advances in materials science and manufacturing are making it possible to build structures in space, rather than launching everything from Earth. And as launch costs continue to fall, the barriers to entry for aspiring space nations and businesses are lower than ever. The potential rewards are immense. The resources of the solar system, metals, water, even energy from the sun, could fuel a new era of prosperity and innovation. But realizing this promise will require unprecedented cooperation, ingenuity, and foresight. As we look to the future, the story of flat galaxies reminds us of the power of natural laws to shape the cosmos over billions of years. The unfolding saga of the space race and the dream of mining Mars show that humanity is prepared to harness those same laws, not just to explore, but to build, create, and thrive beyond the cradle of Earth. The next decades will be defined by how we navigate these opportunities and challenges. Will we become a multiplanetary species, drawing on the resources of the solar system to build a sustainable future? Or will we allow old rivalries and short-term thinking to hold us back? The answers are being written today in research labs, boardrooms, and mission control centers around the world. One thing is clear: the universe is flat in ways both literal and metaphorical, inviting us to explore not just the shapes of galaxies, but the horizons of human possibility. The future of the space race and the prospect of mining Mars promise to transform our relationship with the cosmos, and perhaps with ourselves. The journey has only just begun.